Okay, students. So as I told you earlier, that today our session would be the last session related to the dynamics. And we'll wind up dynamics session today. This portion is this is the last lecture basically for the dynamics portion. And your second midterm will be from the dynamics. So it will be till today. When you meet me after Eid break, the first session will have one quiz, and in the next session there would be midterm. So you can use all these holidays, for example, and the weekends for the preparation efficiently. And since we already delayed our first midterm 2 times, so we do not have any provision to postpone this one. So we'll stick to the deadline for the second midterm. Having said that, students, will go ahead. We'll talk about the remaining concepts. We discussed work done in detail last time, and now we are going to talk about the related concepts, which are basically related to the power and the efficiency of the system. And after that, we'll go forward. We'll look into the formulation for the conservative force and the related energy concepts. So I believe that power, work done, these terms you're already familiar. You have seen it in physics before, right? Maybe not in that detail, but you have seen it already. So are you aware that what is meant by power? Based on your previous knowledge related to the the physics, do you know what is power? Yes, anyone? Any idea, students? What is meant by power? This is the next step. If you have calculated the work done, if you know what is the work done, then if you want to know that what is the rate of work done, if you want to involve in calculating what is the work done per unit time, which is technically the rate of work done, that rate of work done is referred as power, right? So this is the term that came out of the work done, and generally it tells you that what is the rate of the work done, or in other words, it is defined as the amount of work done performed per unit time. So this is referred as power. Power generated by the machine or engine that performs an amount of work done. So for example, if you remember, we use that small differential work done for the small element in our previous session. So here I'm referring it to the same. If you know that this is the amount of work done performed in that small time interval, then when you take it as a rate or as a ratio, that would give you the power involved. Okay. Another way of looking at power is that you know that we can replace this work done as force into displacement, right? Or this is the framework we did last time. So we can rewrite it like this. Students, can you tell me what is this? If instead of writing du, I put the definition of work done here, and then I see them together, this one. What is this? dr over dt. What is the rate of change of displacement?
Velocity.
This is velocity, that's true. So an alternate formula for power could be F dot B. So if you know the force involved and if you know the velocity involved, you can take a dot product and you can calculate the power, right? This is another way. If you know the work done and if you know the time interval, that's another formula. Like this one can be executed, work done over time to calculate power, or if it is not available, then you can use an alternate formula, which is force into velocity. So these are the basic formulation, what you see for the power. Again, we know that for work done, we have the unit of Newton meter, or joule. sorry, Newton meter, and it could be referred as joule as well, if you can see here. And the time unit is second, so that would be Newton meter per second or joule per second. And this is referred as watt. So the units for power is referred as watt. Okay. This is the brief idea of what is power. Uh, what is the significance of power? Like, for example, why we need to measure power in the problems? So we need to understand what's the significance. The significance is that it will provide you a useful basis of selecting the type of motor involved, or for example, what type of machine needs to be there in order to perform certain tasks, in order to perform certain work in a given time. So this gives you idea about that how the input motor would be installed in the system. How much would be the power of that motor that can run the whole system or that can run the whole machine, right? So it gives you very practical insight of that when, for example, if you remember, whenever you are automating there, at the end, there are motors. So how you select motors, practically it is coming out of this power formulation. You figure out that, for example, the power required to run the whole system is, let's say 2 kilowatt, right? And based on this thing, you will select the motor. So you will install motor in the actual scenario or in the actual problem based on the calculations which are coming out of power. And there is one more concept that you will take that is related to the efficiency. I will discuss about it as well. Remember that this is a dot product of force and velocity, and you know that dot product of two vectors is always what? Is always a vector, right? Dot product of two vectors is always a vector, right?
Scalar.
Yes, it's scalar. It's written here as well. And I want to check that who is sleeping and who is just attending the session. So students, take the session attentively. Okay. This is important one. And as I told you, the last two sessions of dynamics are important. So please take it attentively. Are we fine till here? Any question related to this concept of power that we have taken? Should we go ahead? Yes, students, should we go ahead? Any question so far?
No questions,
thank you.
Professor.
Okay, we go to the next concept of efficiency. This is another engineering term that you will see a lot when you are doing calculations. What is the efficiency? It is just the ratio of useful output over the input power. So if you calculate the output and if you calculate the input power, for example, this is referred as efficiency. What do you think? Efficiency should be more than one, right? What do you think? Efficiency should be more than one or should be less than one? What is your understanding about it?
More than one.
Should be more than one. So if at the input, I apply 10 watt, or at the output, I can get 11. Is this what you're saying, Ruby?
I think.
So if I can provide less power in the system and I can get higher power at the output. This is not true. You cannot do that. The input power is always higher. Okay, what you provide at the input, and then there are several losses in the system. So when it comes at the output, it is reduced. Okay, so efficiency is always less than one. This is true. This is not correct because there are some losses within the system itself because of friction, because of heat generation, right? So because of this thing, whatever total output comes at the end, it is less than the input. I give you one example, for example, in the engine. So if you put 1 liter fuel, petrol, and if you calculate the energy coming out of 1 liter fuel, that would be higher. And if you measure the power at the wheel, for example, that would not be equivalent to what you are getting in terms of the fuel power. It will always be reduced. Why? Because there are so many parts moving. It ignites, basically heat is being developed, friction is being there. So that power is reduced, right? This happens generally in all of the mechanical equipment, that at input you have the higher value, whatever you are providing to the machine. And when the machine is giving the output power, it is always less, right? So this is because of the losses, this is because of the friction involved. This is because of the heat generation. And there are many more other wear and tear effects which are there, right? So remember this thing, that this is always less than one. So this is the power idea. It can be represented, efficiency can be represented in the form of power, output over input, or it can be defined in the form of energy, output over input, right? Energy applied to the machine occurs during the same time interval at which it is removed. So energy applied with respect to energy removed from the system can be also used to calculate the efficiency. So this is the important part, efficiency, that you cannot get 100%. Like when you are saying it is more than one, you are telling that its efficiency is more than 100%, which is not true. Efficiency is always less than 100% or less than one, right? If you put 100 as well, as a multiply this thing with 100, so technically you are saying that efficiency is more than 100%, which is not possible. So this is one part. Then how can we solve the questions related to that? So again, the solution of the question is very similar, that first you need to go ahead, you need to first establish the system, the coordinate system. For example, the power supply to the body can be computed using the following procedure: determine the external forces acting on the system causing motion, execute the equilibrium conditions, then figure out how can you have these two, force into velocities, right? Sometimes if the forces are applied in at angle, then you need to figure out the right component of force, right? What you need to take. And once you figure out, you can calculate these formulas, work done over delta T, like time involved, or it can be through the power, force into velocity. So I'll show you, for example, some of the related questions and you can see this thing. So students, the first question is, the man in this figure pushes on the 50 kg crate with a force of 150 Newton. Determine the power determined by the man when t is equal to 4 seconds. Time interval is provided. The coefficient of kinetic friction between the floor and the crate is provided as 0.2. And it is provided that initially the crate is at rest. So this force is being applied at an angle, by the way. Like if you see, you have this 3, 4, 5. Students, what would be the angle here? What would be theta here? If I want to resolve, because I need to resolve the force into the systems, you can see I have established y coordinate, x coordinate, and if you see, the acceleration is towards, like it's moving towards x direction. So acceleration is in the x direction. What would be the angle here for the force? How can I calculate this angle, theta? Yes, tell me. Which trigonometric relation I need to use here to calculate this angle? No idea? Yes, Amir. Hamza, Hassan, Basil.
Yes, Professor.
How do we calculate the angle? Sin theta, cos theta, tan theta. You can
Use
use
the cosine rule, Professor.
cosine rule. Okay. This is right angle triangle. You don't need law of cosine. You just simply use tan theta or cos theta or sin theta. So this would be 3/4, right? What would be that value, students? Can you quickly check? What would be theta now when you take tan inverse?
36.86.
36.86. Let me erase this thing and I can write it again. I don't know why. The cursor is not. Tan theta is equal to 3/4, where theta would be equal to 36.86. Okay. So we figure out that the angle external force is making is technically this 36.86. You can also understand that there is a one component like this and there is one component like this, right? So Fx is equal to F time cos 36.86, for example, and this Fy is equal to F times sine 36.86. Students, first thing what you need to do, you need to figure out like what you have done before. You need to figure out the free body diagram. Once you figure out the free body diagram, then you can solve it into x's and you can apply the equation of equilibriums to figure out the unknown forces. Once you figure out the unknown forces or whatever is the unknown value, it could be acceleration as well. Then you can go ahead and solve this problem. So if I ask you to draw the free body diagram, this external force I have already resolved, right? With the angle. What else should be there if you construct the free body diagram? What else is there? What other forces you see in this problem?
Weight.
Weight, which is acting like this, right? And weight is equal to 50 kg. 50 into 9.81. This will be the weight. What else?
Friction.
Friction. So this F for friction. What else? How you calculate friction? You remember? F is equal to mu times
Normal.
normal force. So normal reaction is missing here, right? So this is equal to 0.2, which is provided mu times n. N you don't know, n you will calculate. It's not provided. So once you establish the free body diagram, the next step is, this is the free body diagram, the same that we have just mentioned, and then you will apply the equation of equilibrium. This time, remember that you are using because this is a kinetics problem, dynamics problem, or more specifically kinetics problem, you need to use F is equal to ma. You cannot say F is equal to summation of forces equal to 0. Otherwise, it will be the statics problem. So you need to use F is equal to sum of forces in X or Y equal to the MA part as well. And acceleration could be in the X direction. Acceleration could be in the Y direction. So students, can you help me in executing this? So for example, if I first go for Y, sum of forces in Y, what should I write? I'm implementing the first in Y direction, this equation. Can you help me in writing that equation? What should I write? What forces you see in Y?
F sine 36.86.
This is F Sine 36.86 plus minus.
Minus.
Yes. This is 1/4. Then what else?
And then minus 8.
Minus 50 into 9.81. What is that value? 490, maybe something like that. Can anyone check? 50 into 9.81 is what?
490.5.
490.5. This is the weight. This is this part, weight. And what else?
And then plus normal.
Plus normal. Okay, equal to. Do you have any acceleration in y-axis? Like, is there any movement happening in a y-axis? Is the crate moving in y-axis or x-axis?
X-axis, so no movement in Y.
So there is no movement in y, no acceleration in y, which means that this is equal to 0. This part is 0. Okay, now can you calculate, students, what is the value of n from here? What is the value of n? Force F is provided here. F that you need here is provided, 150. Please tell me what's the value of n in this case. Yes, students, what's the value? You just simply add these sine 36.86 into F.
580.5.
580.5. So we got the value of normal reaction, 580.5. Now we'll execute the second one, this one. So what should we write for the second equation? How many forces you see in the x direction?
F cosine 36.86.
I will write the value 150, which is F cos 36 point 36.86 and
Minus friction.
minus
So
force
minus
of
mu n.
friction, which is 0.2 times 580.5. And what about the remaining part? What about this part? MA, what should we write? Is equal to?
Equals MA.
M is 50, right? Provided here. And A is AX. We do not know the value. So in this equation, only unknown is AX, right? So you will figure out the acceleration in X direction when you solve this equilibrium condition. Can you please calculate the value of AX from here?
Point 08.
0.08, okay, meter per second square. Okay. So students, you figure out these two. In order to calculate power, what you need is you need the velocity, right? You know the acceleration, you need the velocity, and you can see that this acceleration is a constant value. So it's not like a function of something. So for velocity, you know that V is equal to V naught plus AT. You remember this equation, right? From the dynamics. Now, in this case, the part was initially at rest, so there is no initial velocity. Initial velocity is 0, right? So when you execute, when you put the value of acceleration, acceleration is 0.08. Time is provided as 4 seconds. You can calculate how much is the final velocity that you need here. So what is the final velocity, students, here? 4 into 0.08 is 0.32,
0.
0.32, right?
Yes.
This is equal to 0.32. So you figure out the velocity. Now you have the force, you have the velocity, but remember this thing that the force is at an inclination. It has the inclination angle. So you need to use the force that is in the direction of acceleration, in the direction of motion. So you will be using only x component of force, which is F times cos, which is this part. So if you use this force component and you multiply it with the velocity, how much would be the power in this case? F 150 into cos 36.86, right? Multiply by
38.40.
this will be 38.4, let's say. So this is 38.4 watts. This is the power involved in this whole problem, right? That is technically how you solve the problems which are kinetics related. You utilize the F is equal to ma equation, right? And remember this thing, what we are dealing in the previous lecture and in this lecture, these are the kinetics problem. These are not kinematics problem. Kinetics means that you know that the forces come also in play. Kinematics is when you are only dealing with acceleration, velocity, and displacement, like the initial part of the portion of dynamics that we have taken. Now you are dealing with forces F is equal to ma exclusively for all x's. So this is kinetics problem, right? Is it fine, students?
Professor,
Yes.
why do we not consider friction when we're finding the power?
Because
Shouldn't
friction is already used when we were calculating the acceleration. So when you establish the equilibrium conditions, you know, to figure out the acceleration, it will appear in the equilibrium conditions. But when you talk about, because the acceleration is coming as a result of this thing, right? This 0.08, it came because you already put this acceleration, this friction force there. So acceleration has already the effect of that part. And then you use this acceleration to calculate the velocity. When you go ahead, when you talk about the power involved, the power has already using the velocity coming from the acceleration that has the portion of friction present there, right? So this power is technically not like a net force. This is technically certain force which is externally applied. So the one you have here is the force that is externally applied, and then you are calculating power as a result of this thing, right? So this is a very good question, but remember this thing, that it will not come in play again for the power. It has already been used in the dynamics equation when you calculated the acceleration. So velocity has already this effect that is reduced, right? Like if you skip this thing, the acceleration will be higher, right? And when you use another, when you calculate velocity, the velocity will be higher. So the friction effect of reducing acceleration and velocity is already available in the velocity. So you don't need to include it again in the force. Make sense?
Yes, I got it. Thank you.
Okay. So students, this is first problem. Any other question, or should we go ahead? Is it fine?
Yes, Professor.
Okay. So that's fine. We'll go ahead now to the next problem. The next problem is where you have the power concept and you have the combination of, you remember we discussed one topic related to these pulleys and ropes, right? The absolute motion analysis, that topic. So this problem has a combination of the absolute motion analysis, and also at the same time it has this power concept present there. So students, now in this case, in this problem, it says that a motor M of the host operates with an efficiency. So the motor efficiency is provided, which is present here, this one. Determine the power that must be supplied to the motor to lift 375 Newton crate. So this value is provided. It's not provided in terms of mass. It's already multiplied by 9.81 and you actually know the weight this time. It's not mass. At point C, at the instant point P on the cable has an acceleration. So at this point, the acceleration is provided as 1.2 and the velocity is 0.6. So you need to figure out that how much power is needed by the motor in order to lift the crate. However, initially we assume that the crate is moving downward, right? It is going downward because of the action of the weight, whatever it is, and then this is the motor power that is included. So students, in this case, again, first thing we need to do, we can take the free body diagram involved. This free body diagram is related to this part. If I construct the free body diagram, I know that weight is acting downward here. And at the same time, I know that there is a tension, like there is a tension here and there is a tension in the rope here, right? So technically speaking, if I can say that in the upward direction, there are 2 times tension present because there are 2 ropes present. And the weight is acting downward. So I can go ahead, I can build the first equation, for example, the equation of the equilibrium. I can say that sum of forces in y direction is equal to my. So in order to have the acceleration, keep the acceleration positive, what I did, I use the downward direction as positive here. You can flip it as well, and the final result will be the same. It will not change. Only the thing will be that 2t will become positive and this will be negative and a will be negative in this case. So when I say how many forces you see in the system, students, when I execute that equilibrium condition for the crate itself, you see that there is only upward tension, which is here, right? As per my convention, I'm taking it negative because my convention is negative here. And this will become positive. So this crate weight is there. This is nothing. This is just the mass of the crate. So you know that you have the weight provided. When you divide it by 9.81, it will convert into mass. So this is nothing. This is just the mass. Acceleration at point C, I do not know. So I will figure out once I solve this part. So this is students, the first equation, you can say that. Then do you remember, students, when we solve the absolute motion analysis, we were using the length of the rope in order to figure out accelerations. So do you remember that what we did that time? Anybody who can tell me how can I take, like, which parts I need to ignore here of the rope, and what should I write in order to have the equation of length of the rope? Do you remember that we first placed datums? And this datum is towards the increasing distance of the rope, right? So this will be increase in this direction as, let me erase it and do it again. So this is the datum point here. This is increasing this way. This is the datum for the other rope. This is increasing this way. So which parts we ignore? If you remember that discussion, which part of the rope we ignore in the total length, or that will stay constant? Yes, students, any idea? Should I keep that part of the length, part of the rope? Should I keep this rope? Should I keep this rope? When I build the equation of length of the rope, should I include these highlighted regions or no?
No.
Because they remain, because why? They remain constant, right? So you ignore these constant values. This is again the topic of absolute motion analysis. and we solved several problems only in that session. Similar one. The length, total length would be equal to, what should I write? The total length is the one that I'm highlighting now.
Two SC.
2SC
Then
plus
1 SP.
1 SP is equal to the total length. Right? Can you see it? I highlighted it on the problem as well. So the length of the rope that you need to take into account that can change with the time is only this part. SC can change because the datum has been established, and the other rope can also change. SP can also change for point P. Students, make sense till now? So if I take the first derivative, what would happen? Now I have the equation of displacement, or more like length. So when I take the time derivative, first time derivative, right? It would be dl over dt 2 times dsc over dt plus dsp over dt. So what is this? What is this? And the total length will change with respect to time or no? When I take the derivative, is there any rate of change involved on the total length? The total length is a constant, right? It's a constant value. It will remain 0. However, this can change. For the distance SC can change, the distance SP can change. So generally, this is 2 times velocity at S plus this is velocity at P. Then what you do one more derivative because we need acceleration. So when you do one more derivative of this equation, this will reduce to 0 is equal to 2 times AS, AC, in fact, it's not SC, AC plus AP. Or in other words, when you rewrite, you got the expression of that AP is equal to minus AP, or AP is equal to minus 2AC, right? You got this equation. Now, if you see, the question is giving us this value. The acceleration is provided for point P as 1.2 meter per second. So we technically know the acceleration at P, and using this value, we can calculate how much is AC, right? So this is what we did here. If you see, we developed the equation. The way we developed the equation is here. I have shown you the working for that. And then you plug the value AP as 1.2. This is provided in the question. And the value of AC reduced to minus 0.6. Okay. This value of AC now, I can place it here into the first equation, the one I developed. So in the first equation, there were 2 unknowns, so I would not solve it. Now I know the value of AC, so now I can solve the value of AC and I can get what is the tension involved. The tension is around 199.0 second. Sorry, 0 Newton. So I know the tension in the rope is 199 by using this analysis. Is it fine, students? Are we clear till here?
Yes.
Yes.
Okay. Then the next thing is, once I know the force, I can change it into the power as well, right? So here, this tension is nothing. This is just like a force. So taking force, product of force into velocity, velocity value is also provided. That velocity is 0.6 at this location P. So I know that the tension in the rope is, for example, 199 and the velocity is 0.6. So just taking the product will tell me that the value of power is 119.4 watt. Now, student, one important thing you need to understand that this is the force, this is the power 119, which is required in the system, 119.4. This is what you need, right? So think of that this is the motor. This is the input. This is the input. This is the output. So at output, what you need this much power, right? So how much you need to provide it at the input? This is where the concept of efficiency will come. So if what I mean to say is, again, you need to understand the concept that think of this as motor. At the input, you need to provide power. At the output, you need to provide power. So point P is technically the output. You know that 119.4 watt is required at the output, right? Input should be higher or lower? The input power should be higher because I told you, I just mentioned you something that there are always losses within the mechanical systems, right? So whatever is input, you don't get it at the same output. Same value is not there. It is in fact reduced. So at the output level, you know that 119 is required. So at input, should it be lower value or should it be higher value? Like efficiency is input over output, right? Sorry, I flip it. Sorry, it's so what should I do now? I know the value at the output is 119, right? And I want to calculate the value of input. What should I do? And you know the efficiency is as well. The motor efficiency is provided to be 85% or in fraction 0.85. So what should I do? I will divide 1.4 with 0.85. So I would know that the input value of a motor should be around 140. So that keeping in view that its efficiency is 85%, I will get the output value at 190. This is what I need at the output, right? So the input value should be higher based on whatever the efficiency is. So motor efficiency could be 90%, could be 80%, could be 70%, 60% whatsoever. Based on this thing, the input requirement will increase, right? So remember this thing that you need to include this thing into the problem. Yes, students, make sense so far? Did you get this idea of efficiency?
Yes, Professor.
Okay. So this is the one. Then students, there are some more concepts which are very specific to energy. And when I talk about energy, I'm talking about more like potential energy. In order to understand the potential energy, we generally get one concept. This is called as conservative force. So conservative force is the force, for example, when it is performing some sort of work, it does not involve or it does not take the movement of particle or the path taken by the particle from moving from one point to another point. So it does not involve any consideration of path required. If, for example, initial position is here, final position is here, like the path can be taken like this. For example, I'm just giving you rough value. Here you don't consider the path. Here in the conservative forces, the path does not mean anything. You are only concerned with the initial state and the final state. Only the first positions are required. When you're dealing with such problems where the path is not required, only the states are needed, initial and the final state, then these are referred as the conservative force. It is defined by the work done in moving a particle from one point to another that is independent of the path followed by the particle. So you're only concerned with the movement, initial state and the final state, but you're not concerned with the path taken. So in this case, only initial and the final states are required. What is energy? Energy is defined as a capacity of doing work. right? So kinetic energy is associated with the motion of the particle. We know these basic definitions of energy and the kinetic energy. Now, if I talk about the gravitational potential energy is a classical example of conservative force, that you're only concerned with the amount of work done based on only the states, the position, that where the initial position is, where the final position is, right? So generally what we do, whenever we are solving these problems related to potential energy, you know that potential energy is equal to mgh, right? Or if I say more specifically, this mg is technically weight into h. Can be height, h can be any other vertical parameter that can be used, right? So here in this problem, what you do, the more important thing is that you always need to establish a datum. So you always need to set the ground. In our generic approach, we set the ground level as datum, and then we measure the height, right? But this is up to your choice. You can change the datum if you want. And if you are moving in the positive direction of y, like height wise, then generally we say that this is the positive potential energy, positive gravitational potential energy. If it is in the negative side of the datum on the other side, then it would be referred as a negative potential energy, right? The magnitude is given as mgy or wy or mgh. It's the same thing, in fact. But remember that it is referenced with the datum, and there is a possibility that it can be in the positive side, it could be in the negative side. So the two differences when you calculate, you will involve the right notation in that. Then students, we also have another form of potential energy coming from the spring. So this is called as elastic potential spring energy. When an elastic spring is elongated or compressed from an unstretched position, the elastic potential energy is. Here students, this is the value of, this is how the energy is stored within the spring. This is for the linear elastic spring, it is provided. You remember it is very similar to what we have derived for the work done formula, right? So it is very same, half ks square. So this is the energy when we are calculating energy in the spring system. One thing you will understand here, think of that this is unstretched position. So this is where the value of V is 0 because S is 0. S is 0 here, that's why the whole system is 0. When I try to stretch it in this direction, this is the positive distance, because again for me the datum is here where it is unstretched. This is the datum point for me. S is positive in the elongation side, S is negative towards compression. But students, do you think that positive distance and negative distance will make any difference here? Do you think that it would make any difference? The positive value, like the energy can be different, or it will change if it's a positive value or a negative value?
No, it won't.
The reason is, what's the reason?
It's scalar. Distance is scalar.
It's path independent.
And the other value is that the datum is provided, by the way. Don't forget the datum is telling you this is a positive S, this is a negative S. But you remember this thing that this is a square term. So when it is a square term, it will always come as a positive number. And you know that this is always be positive in this case. Potential energy will always come as a positive number. Okay, so remember this formula, see this formula. Sometimes students, we have a scenario where we have both type of potential energies present within one system. So we have, for example, this weight is hanging, and let's say this is 100 kg, right? Now with respect to datum, we know that if we know the distance y, for example, the weight is there, we can calculate the potential energy, right? The gravitational potential energy. So in this case, there is a stretch within the spring as well, and there is a weight involved as well. So Wy will also be there, right? Positive or negative depends on the datum position. And similarly, the other value will also be there. So we call this potential function together. In combination, when both are present, both type of potential energies are present, it is called as potential function. Okay, and it is technically represented like this. This is the gravitational one, and this is the elastic spring elastic potential energy. If the particle is moving from one state S1 to any other state S2, for example, lower position in this case, then you remember that you calculate this one for the first state minus again the second one for the second state, right? So you will do first calculation for the stage one, then you will put this one for stage two. And again, if both are present, then you need to figure out, you need to have both components. This is the MGH, for example, for the gravitational, WS1 minus WS2, and this KS1 square minus KS2. So you're taking like a difference of both potential energy parts. So this is technically the work done involved. If you want to calculate the work done, this is how the work done can be calculated within the difference in two states or positions. Work done by the conservative force can be written in terms of the difference of the area. So this is what you have written, that the work done for the conservative forces can be expressed like this equation. This is the equation that can be used to calculate the work done by the conservative forces, that can be written in terms of the difference of their potential energies. So when you rewrite the difference of the potential energies, you can talk about the work done. If only conservative forces are applied to the body when moving from state to state, we have this one. So students, this is true for the conservative forces. For the conservative forces, what I'm telling here, that for state one, the kinetic energy and this potential function. So this potential function has further Vg plus Ve, the gravitational and the elastic part. I am saying that this is state one. If I make a sum out of these at state one, it would be equal to the sum of these energies at state two, right? So this T2 is technically the kinetic energy, and V2 is again, which is the sum of the potential function, which is the potential function sum of the gravitational potential energy and the elastic potential energy. So at any states, if I have two states, 1 and 2, I can say that the kinetic energy plus the potential energy through gravity plus potential energy through the elastic 1 at this stage is equal to the kinetic energy of second stage plus potential energy of gravity plus potential energy of elastic spring. At any state, when you take sum of these two and you take sum of these two, the total of energy will remain at any stage will be the same. Maybe they vary only in the numbers. Maybe here this is 10, maybe here this is 5, this is 2, the total is 17. When you go to the other stage, maybe kinetic energy is 5, maybe potential energy becomes 10, maybe this is 2, or maybe I just change the number 8 and 4. So the sum remains at any two stages the same. The total energy remains same within the system at any two stage. This is called as the conservation of mechanical energy or conservation of energy principle. I think you have taken this thing in physics when you were dealing with the pendulum, simple pendulum, or when you take the example of this object that is falling from the height. So if the datum is at the floor, students, you remember that if you talk about the potential energy, there is no spring energy here. It's only the gravitational potential energy and kinetic energy. When the object is starting from rest here, what is the energy? What energy levels it has? When it's starting from the rest, this is stage one. What do you see? How many types of energy I need to write here?
Just potential.
It has just potential because this is the height from the datum, right? This is the height from the datum. So this has only mgh. And as we started that this is coming from the zero, this is coming from the rest. So there is no kinetic energy because velocity will be zero. So there is only value of mgh. When it reached the middle, so it starts moving, it went into the middle. What type of energies it has? What energies it has for the second state?
Both.
Both kinetic and potential.
This is first stage. Second stage, it has both mgh2 plus kinetic energy 2. When it reached the second stage, do you think that the potential energy is same or different with respect to the first one?
Different.
It should be less.
Should be less because the height is less, right? So where this remaining energy will go, it will get converted into kinetic energy because velocity is there now, right? And when it go and hit the floor, this is the third one, third stage. What type of energy it has? Only
Kinetic.
kinetic. The height becomes 0. However, the velocity increased as it moved downward. So all of the potential energy you can say that get converted into that. Now, if you get this value 100 here the total value will always be 100. Here it will always be 100. So you cannot create energy, you cannot destroy energy in the systems, right? So that will remain conserved, or that is referred as the conservation of mechanical energy or conservation of energy principle, right? Specifically for the conservative forces. So this is how it is mentioned. If it is true for one particle, it's true for the remaining for the system of particles as well, right? Generally, we know that the summation of this at any state is a constant value. They might fluctuate, T or V values can fluctuate, but the total will remain the constant. So these are some of the same principles. Go through these procedure of analysis. It's very same what we will explain, but as we go forward, we'll see now how can we implement the solution related to that. Are we fine, students, still here? Any questions so far? Any question that you think you need further explanation or anything? Are we good to go?
No
Yeah.
questions, Professor.
Okay, now let's solve this problem related to the same conservation of energy. So this is the gantry structure, which is used to test the response of an airplane during a crash. So this is like kind of a test bed for the crashing mechanism of the airplane. So the plane of mass 8, what is this unit? What is this unit? 8 mg is what?
Megagrams.
Megagrams, which is 10 raised to power 6, right? So if you want to rewrite it, because you know that in most of your formulas, you need to write kgs. So how many kgs it would be? How many kgs would be? 8,000 kgs, right? This 8 megagram is equal to 8,000 kgs because it is 8 10 raised to power 6 grams. I can rewrite it 8 10 raised to power 3, 10 raised to power 3 grams. So technically this is 8,000 and 10 raised to power 3 can be referred as kgs. So that's understood, right? That 8 mg is technically what? Is equal to 8,000 kilograms. Is it fine, right? Okay. The is hoisted back until the theta is 60. So this theta is provided to be 60 here. And then pulled back cable AC is released. So then you will release this cable. So this is broken or not broken. In fact, I think it will stay. When the plane is at rest, determine the speed of the plane just before clashing into the ground, which is around this angle, which is 15. So you need to determine the speed, this speed, when the angle is 15. Also, what is the maximum tension developed. So you need to figure out the tension in the rope, in the supporting cable during the motion. Students, one thing you need to understand, this is what type of motion. Like you have seen previously, you have analyzed the rectilinear motion, you have analyzed the curvilinear motion, right? So what sort of motion this is?
Circular.
This is circular or curvilinear, right? And in the curvilinear motion, you know that we have taken x, y, we have taken rectilinear coordinates, we have also taken the tangential and normal coordinates as well, right? So easier for me is technically if I work with the tangential and the normal coordinates for this problem, because this is circular problem, right? So I can take this towards the normal axis and this is the tangential axis. So if I solve the problem related to these two coordinates, it would be easier for me. So one thing, student, that I need to do, I need to apply the conservation of energy first. I need to say for state A, TA plus VA, this is for state A, is equal to the sum of energies which are happening at point B just before the crash, right? A is the condition which is here where the angle is 60. B is the stage here where the angle is 15 degree. See, right? So this is the part. Okay. Then what I will do, I am going to consider, for example, the free body diagram of the plane. So free body diagram of the plane, it will look something like this. Think of that the weight, this is where the tension is present, right? And this is the neutral axis and tangential axis is here. And students, think of that weight is acting downward like this, right? So in this case, this angle would be, how much would be this angle? With respect to normal, this, how much this angle will be there? Like you have this line here, straight line. And if you draw vertical, this is 60, right? So same is the scenario here. This line of action for the normal is the same. And the vertical is acting downward. So this angle should be equal to 60, right? Can you see the angle 60 or should I explain it again? Yes, students.
You can see.
I can again show it to you very quickly that this is the normal axis, right? This is the normal axis. Tension is technically here. And you see that line of action is going like this, right? So if you put any vertical line, that angle is 60. So if I draw, for example, the weight is again just like the line of action is 60. This should be 60 degrees, right? Weight is 60 degrees. Tension looks like this. Yes, students, make sense?
Yes.
Okay, now if we look into that, we are now going to talk about the what is the value of TA, you think? At location A, what is the kinetic energy when it started the test?
0.
0, because velocity is 0, right? What about this potential energy? For potential energy, the system, the picture is showing you datum is here. The datum is fixed here. So technically speaking, you need the distance, which is still this part, right? This height is needed. So what is this height, students? How can you figure out that height? How can you figure out that height?
With the cosine.
20 is given. Like if you take it like a triangle like this, 20 is there, right? And or 20 is here. This angle is 60. So technically speaking, you need this length, right? So this length is equal to 20 cos 60. So this side you will say kinetic energy is 0. And this is below datum. So this will be taken as a negative value, negative potential energy, because this is below datum. And it would be equal to mass 8,000. Its weight technically mg, so 9.81. And what's the distance? Distance is equal to 20 cos 60. Is there any other thing you need to write for A? State A? No, right? This is done. Then students, you need to write the state for the B. So when it moved from here to here, this location B, what is the kinetic energy? What should I write for the kinetic energy? Yes, students, what should I write for kinetic energy, this part?
Half times 8,000 times VB.
Half m v square. So VB, you do not know right now. Like this is the velocity. So you do not know right now, you will figure out this thing. And this will be used later on in the computation. What should I write for the gravitational potential energy? This is the kinetic energy, TB. For the VB, which is the representation of potential energy, it would be, what should I write for that? I will write here minus. This time you need which distance you need, students, this time? This is 15. It's here, and you technically need this distance. So this is 20 times cos 15, right? This is the distance, this is the height. So it would be minus, what should I write? Minus 8,000, 9.81, and this is m, this is mg basically, and height is equal to 20 cos 15. So the total equation, this is the remaining part from here, by the way. So if you solve this equation, what would you get, students? What are you going to get? The value of velocity at B, right? Why we need velocity at B? Because when we put the analysis here, T, when we put this analysis, we will do equilibrium here in normal direction. We need the value of centripetal acceleration. You know that we need acceleration in that direction, in the direction of normal. So that velocity in the at B will give us this value. The centripetal acceleration will be provided as a result of this thing. Right? You remember what was the value of centripetal acceleration? So first tell me what's the value of VB from this equation?
13.5.
13.5. VB from here is equal to 13.5. Okay. Now, once I got the value of VB, you remember that we discussed the free body diagram here. Like I draw it for 60, but it's the same for 15 as well. Right? So at VB, for example, you can draw this let me erase this one quickly. So at this one, it's the same, that you have tension here. This is the tension in the rope, right? The weight is acting downward, right? This is the normal axis. This is the tangential axis. This is angle 15. So when you redo it, because you have the velocity at B, the free body diagram will look like this. This is the free body diagram, right? Weight is acting downward, 8,000 times 9.81. Angle is 15, T is there. What you do, you put the F is equal to MA in the normal axis, right? So sum of forces in the n direction, how many forces you see in n direction? How many forces are there, students, in the direction n? T is there, and the weight, which is the component of weight, right? Which is this one. This is cos component or sine component for a weight?
Cos.
Cos, yes. So this is weight is 8,009.81 into cos 15. So this will be T minus 8,000 into 9.81. This is the weight. And then this is cos 15 is equal to M. So this is MAN. AN, remember, in the normal axis, you don't have you have the centripetal acceleration. So what was the formula for centripetal acceleration? V square over rho, if you remember. The initial part, when were solving the normal and tangential component, so we said that AN is equal to V square over rho. So M will be 8,000, right? V is, we have calculated here, 13.5. Rho is the radius of the curvature. This is the radius of the curvature, rho. This is 20. It's provided as a radius of curvature. So we have all the thing, and as a result of this thing, we can figure out the tension in the cable. So that came out to be, for me, is 145 kilonewton value. So students, that's basically how you can use the conservation of energy, and you can solve the unknown values, right? Here, I think the question was asking what is the maximum tension. So you figure out T and determine the speed. So you figure out the speed VB, you also figure out the tension in the core, right? This is the processing. Students, any question? Did you get what we have executed here? Any question related to this problem?
No, Professor.
Okay, so this is the one. Then we go forward for the next problem. Next concept, students, is the concept of principle of impulse and momentum, linear impulse and momentum. Right? So again, we'll start from that F is equal to ma equation, the basic equation. You know that acceleration here can be rewritten as this, the derivative of velocity. So if you write acceleration as a derivative of velocity, and then later on take this delta t towards the side of the force, here you will only stay with mdv, right? So it will look like this, f dt, and here m is a constant, so m will come out and dv will stay, and then you put the limits to solve. So this is a differential when you want to solve it for the time interval, for the interval, for example. Then here with respect to delta t, you have a time. Here with respect to velocity, you have the initial and the final stage of the velocity. So when you open, students, you will end up you will end up like this, mv2 minus mv1. Like when you solve the integral here, it will become as v, and the limits would be v2 and v1. Eventually it would be v2 minus v1, and when it get multiplied, it will look like this. Now, do you remember that mass multiplied by velocity is, what do we call that? Mass into velocity?
Momentum.
This is momentum. So this mv2 is the final momentum, mv1 is the initial momentum. And students, this side, when you have only force, when you have a force as a product with time, right? This is called as impulse. This side is impulse. This side is the difference in momentum, right? Linear momentum. So this equation collectively called as the principle of linear impulse and momentum. This alternate form of Second's law, which translates into this, which is the difference of momentum on this side, is equal to the impulse on the other side. That is referred as the principle of linear impulse and momentum. The vector, so linear momentum, students, you see that this is a vector quantity velocity, this is a scalar quantity. So when scalar get multiplied with a vector, it remains scalar or vector?
Becomes vector.
It's a vector, yes. If scalar value multiplied with a vector, then the resulting is also a vector. So here velocity is a vector, mass is a scalar value. When it get multiplied, it gives you the vector which is referred as linear momentum, right? And it is in the same direction of velocity. So linear momentum has the same direction as velocity. And the units are, this is velocity units, this is mass unit. So it is kg meter per second. That's the velocity of, that's the unit for the momentum, linear momentum. On the other hand, if you remember, I told you that this side is referred as impulse. So this side is referred as impulse. Generally, capital I is the symbol. It's called linear impulse. And it is the measure of the effect of force during the time of the force acts. So it is not only the force, it is telling you the information of time as well in the same time, right? It is telling you that collectively that this force is being applied for this much time. So it has the information of time. So impulse is not only the force, it has the information of force plus time interval as well, right? So this is called impulse. The impulse acts in the same direction as the force. Magnitude has the unit of force time, which is Newton second. If the function of force is changing with respect to time, then you know that you need to work with the integral. Then when you calculate impulse, it is through the working of integral, because f is a function of time. But if you are dealing with a constant force, which is not a function, then you know that the function will reduce to a straight line, and you are more dealing with the time interval, which is simpler to incorporate, t2 minus t1. So when the force you are dealing with is a constant number, then you just simply use the time interval as t2 minus t1. Otherwise, you need to use proper integral when the force is also a function of time, right? So remember that part. So students, what we do, we generally shift that part here. So we write it like mv1 plus impulse is equal to the final momentum. So if I rewrite it, the equation will look something like this, right? This is the initial momentum, this is the impulse term, and that would be equal to the final momentum, right? Remember this thing, that once the problem comes, you need to extend this equation into all axes. So you will solve it for x-axis, you will solve it for y-axis, you will solve it for z-axis. Depends on that how the problem is. Most of the times what you are looking at in this course right now are the 2D problems. So you need to execute the equation of linear impulse and momentum for 2 axes at least, right? Here again, if I show a pictorial description, so this is the initial momentum, which is referred here, mv1 is shown on a particle. V1 is the direction of velocity. You can say that V1 is in this direction. Then the force is applied with respect to time, that is shown here, the impulse term. And then the final resulting momentum is here. This V2 is in their direction here, shown here. Force defines the direction here for the impulse as well, because this is also requiring a direction. So the vector notation come from the force. Here the vector notation of direction comes from V1. Here the direction of this thing comes from V2, right? So this is kind of the idea related to the principle of linear impulse and momentum. Again, you need to first draw the free body diagram. You need to draw the sense of initial and final velocities. You need to know that these velocities are positive or negative sides. And at the end, you will draw some diagram like this. This is called impulse and momentum diagram, right? Where you show the final scenario, that what is happening based on these three quantities. I will show it to you now. It's very similar, this idea. I'll skip that part and I'll quickly go to the problem solving now. So students, this question tells you that a 100 kg stone is originally present at rest on a smooth surface. Okay, and if a towing force of 200, if a towing force of 200 Newton acting at an angle of 45 degree is applied to the stone for 10 seconds. So T is provided as 10 seconds. Determine the final velocity and the normal force which the surface exerts on the stone during the time interval. Okay. So, okay, we need to calculate the normal force and we need to calculate the final velocity for this one. The biggest hint for you is in the problem when the time interval is provided here, that the force is applied for 10 seconds, which means that the information is provided to you in the form of impulse, right? So impulse is provided. First thing, students, you need to draw the free body diagram. So how you draw the free body diagram, you know that this is the object. This is currently having a towing force of 200 Newton. This is 45 degree, right? What else I have, students, here? What other forces I have? What other forces are there in the system?
Weight.
Weight is there, which is, how much is the weight? 100 kg. So 100 kg means multiply by 9.81. It would be
981.
981. That is the weight. And what else? It should have a normal reaction, right? One thing is that the question doesn't show you, doesn't tell you anything currently related to there is no information of mu, right? So if mu is not provided in the question, it means that you don't need to include the friction. If mu coefficient is provided, then it is the indication that force needs to be in the picture. Friction force needs to be in the picture. But if it is not there, then you don't need it. So students, now we need to put MV1, like the formula is MV1 plus sum of all forces and the time involved, time interval, is equal to MV2, right? And you know that this is a 2D problem, so we need to use it for x-axis and we need to use it for y-axis. So when I write first for the x-axis, right, think of that you're rewriting this equation for x-axis and it has velocity information in it. So I'm saying that velocity is positive in the positive x direction. So what should I write? Can you tell me, like, for x, what should I write now? What is the initial momentum term here for this problem? The 100 kg stone is originally at rest. So what should be V1x? What is the initial velocity?
0.
MV1x should be 0 because it's starting from the rest, right? Then, for example, in x direction, how many forces you see, which are present in the x direction? How many forces in the free body diagram are in the x direction? 981
One.
weight is vertical, NC is vertical. 200 Newton towing force has two parts, right? So it has this one part, which is an X. So this is 200 cos 45. This is 200 sine 45, right? So you have only one component like this. So when I write this second term, I will only write is as it is 200 cos 45. Time is provided as 10 seconds, right? So time is 10. And what should I write for the final one? The final one is M, I already know, this is 100. V2, V2x is not provided. V2 is not provided. V2 is what I will calculate, right? So there would be final velocity that I will calculate, V2x. So students, can you get the velocity out of this? What would be the V2?
14.1.
14.1. Remember one thing, students, that the stone will move like this, right? Only in x. So this V2, what you have calculated, V2x, the final velocity is only in x direction, by the way. It is not moving in y direction, right? The stone will move only in x. So what you have calculated in x, technically speaking, this is the V2. It doesn't have any y component. So this final velocity, what you have calculated, is coming from here, right? The stone will only move in only in x direction. So it only requires x value of the final velocity. Then students, you need to redo it, rewrite the values again, but this time for y. Same principle, apply it for y-axis. So for y-axis, what should I do? mv1y. Is there any v1y? Is there any initial velocity in y direction?
No.
No.
Started from rest, right? So it's same. Both will be 0. This is 0. But now this time you need to carefully involve all of the y components. So the first force is minus, because this weight is acting downward, my initial is positive upward. So I took 981 into 10, weight into the time. This is one component of force. Then what else? Plus NC into 10. This is the normal component, normal force, plus what? 200 sine 45 into 10. And what is the final part here? mv2y. What is the final v2? Is there any y component of v2? Is there any velocity in v2? Final velocity in y-axis?
No.
So this part at the end, mv2y, is also 0, right? Because there is no velocity component in y-axis. It's moving only in x-axis. And x-axis you have already figured out, it's 14. So if you see this thing, the only unknown is normal reaction. So if you solve this one, you will figure out the value of normal reaction. If you quickly do a calculation, can you tell me what are the values? What's the value for NC here, normal reaction?
840.
840 newtons. So this is 840 newtons, right? This is the answer. So you calculated the velocity V2, final velocity. V2x is technically the final velocity, and the normal reaction is 840, right? This is what you have here. I have already solved, but it is what you have here as well. Any questions, students, related to the application of this principle? Any question?
No, thank
No.
you.
Okay, so this is fine. Can you guys try to solve this thing at your own? The time interval is 0.15, by the way. This is 0.15 s. I will wait for you. You need to solve this question at your own. And you need to tell me, for example, what are the final answers related to that. The equations you need to put. Again in x-axis and again in y-axis. First, tell me that what is the question asking? What you need to calculate? What is the final? What do you need to determine in this question? Because here velocities are provided. Initial velocity is provided, final velocity is provided. So what is needed here?
Impulse.
Impulse. What is determine the average impulsive force? So technically, what is that force which is in the impulse? Because time is also provided, right? Time 0.15 second is provided to you. So you need to first execute this equation for x-axis. This will give you fx. Then you need to execute for y-axis. This will give you fy. And once you know what is fx and fy, you know that factor f is equal to fx I unit vector plus fy j unit vector, right? If you want to know the magnitude, the directions, you can calculate from the vector formulation. You know that f magnitude would be equal to fx square plus fy square. So when you resolve this equation, it will give you x component of force, it will give you y component of force. So this is what you need to do, right? Okay, this part separate. So I will write it for x now in front of you. I'll take the positive x direction as a positive. So students, now what I need to write mass times v1x, right? Plus fx t is provided 0.15 and I need to write m v2x, right? M is provided as, what is the value of M? Mass. What is the value of mass, students, here in the problem?
0.5.
0.5. What is V1x? V1 is this. What is V1x? 80, right? But remember that it is going into the negative x direction. So it should be negative 0.5 into 80. V1x is 80. Plus fx, you do not know. Time is 0.15 provided. M2 is again, M is again 0.5. Mass is provided for the baseball. And what is V2x? Now, after hitting the ball is moving like this. So technically speaking, this is 120, right? Angle 40, which means it has one x component, 2 cos 40, and it has one y component, 120 sine 40. So which one I need to pick here for V2? V2x?
Cosine 40.
Plus or minus? This is positive
Um,
x or negative x?
Positive.
Positive x. So it will stay 0.5 into cos 120 into cos 40. Once you solve this equation, you will figure out the x component of force, impulsive force. What is that value? Can you quickly check, students? What is the value of fx here? Yes, student, what's the value? Fx
270.
Fx is 270. Students, can you
Oh
check?
no, wait, 1 second.
I got it as 573.
What is this value? 120 into cos 40. What is 120 into cos 40?
92.
42?
92.
92. 92 times 0.5?
45.9.
45.9. And this is 40, right? When it goes on the other side. It would be 40 divided by 0.15. So how much is that value, students? What value you mentioned for fx?
$573.
573. Is it correct? Everyone is getting the same number?
Yes, I got the same.
Okay, now you need to do the same thing for y-axis. So let me erase this thing a little from here. Same equation for y-axis. M, here I will take the upward direction positive for velocity. So m v1y plus fy into 0.15 and equal to m v2y. So students, is there any y component of v1? This is coming in the x direction only, right? At used in the first case here. Is there any y component for velocity 1? When the ball is
No.
moving with 80 meter per second, it's only in x direction, right? So there is no component, which means this is 0. And fy 0.15 will remain the same. What should I write on the other side? It should be 0.5 into 120 sine 40, right? So what is this when you solve it for fy? How much fy will be present? (120 into sine 40 into 0.5 divided by 0.15. Yes, students, what's the value? What's the answer, students? What's the answer, students? Did you get the answer for fy? What's the value?
I got 257.
257. Okay. So this is the x component, right? And this is the y component. You can calculate the magnitude of the force by using these two, right? And if the question asks you to write it properly in the vectorial notation, you can write it in the vectorial notation as well with the proper angle. You know that if you know f, x, and y, you can also calculate the angle theta out of it. Same vectorial calculation that you have done previously in chapter number 2. So students, technically speaking, this is the idea of how you implement the principle of linear momentum, linear impulse and momentum. Okay, make sense to you?
Yes, Professor.
Okay, so I think that's all for today. That's how we have finalized the dynamics portion. Okay, and what I will do, I will assign you the next homework, which is some problems related to what you have seen today, some problems what you have seen in the last lecture. Okay, so I will not make it very extensive. I'll just maybe give two problems from each lecture. So I will not make it very extensive homework, but if you focus on what we have solved in the class, that's very important. And it has a lot of questions in both of my classes, today and the last one as well. So focus on what we have done in the lectures, and I think that's a good practice for you. So if there is no question, I will wind up the class for today.
Professor, when would the homework be due?
So homework will be due on the weekend after the Eid break. Right? So you have the next whole week off for the Eid. So I
Yeah.
will make it basically on the weekend of the very last, maybe, Sunday night or something like that.
All right. So right before the quizzes and midterm, yeah?
Yeah, quiz, I am thinking that maybe I not include today's class. So I will just restrict it to the till last session class. Okay. And this way you have more flexibility. So this last lecture, you can also do the calculations, for example, for your, so you will have more time for the quiz, you can say that. Quiz material, I'm thinking not to make it today's class included. Maybe I will just include it till the last week, right? And maybe by the end of the submission, like when you need to do the submission, you only do the submission for the numericals that you have taken till the last week. So today's numerical, for example, we can extend the homework for these 2 or 3 problems. We can make it before the exam. Okay,
All right, okay.
I will look into it. I will schedule something and then I will give you guys an announcement.
All right, thank you, Professor.
Professor,
Yes.
where can we find the recordings of this class and last class?
This is with me. I will upload it.
Okay, thank you.
Okay, so let me just quickly take the screenshot for attendance. Okay, students. So I think we are fine for the day. Just good luck for the quizzes and the exams. And again, if you remember the style, what you have seen in the previous quizzes, the class problems are important. So having said that, I will just wind up the class for today. Take care and good luck. Bye.
Thank you, Professor.
Have a good day.
Thank you, Professor.